Hi, I'm Amy Williams. I am a middle school science teacher at Headwaters Academy in Bozeman, Montana, and I am a longtime Nano Days volunteer, and I also have my students trained every year to volunteer with me at Nano Days. So I'm going to show you a couple of the Nano Days activities that we do and that are included in your teacher's kit, so you have a better feel for how to do the activities and some of the background concepts you may want to explain and cover with your students. We're going to start out with the activity called Thin Films, and this is a fun activity everybody loves. Things you might need to explain or refresh, ideas that you might need to refresh with your students before or during the activity are the concepts that light travels as a wave, that waves have crests and they have troughs, and the distance between successive crests or troughs is called the wavelength. You'll want to review the fact that white light is actually made up of 7 different colors of light, and that's the visible spectrum, and that each one of these colors has a different wavelength associated with it. You'll also want to review the fact that waves can hit a surface and then reflect back. We call this constructive and destructive interference. So there are a couple steps in this process, and so I'll go through the process. First, you want to start with the black slips of paper that have been included in your kit and one of the silver Sharpies that you'll get as well, and have each student write their name on the piece of paper, like so. And this is actually just so they can identify whose is whose at the end. The next step is you immerse the paper totally in water and keep it down underneath the water. And then you get your nail polish and put a drop or two on top. Just so it makes a sheen on top of the water. I actually got mine on the paper. That's not ideal, although it's not a huge problem. And so you keep the little piece of paper in the water and then slowly pull it out. And I don't know if you can see this, but it coats it with a very thin film of nail polish. Okay, and then you want to put it on the paper to dry. Ideally, this works best when you let the paper kind of sit sideways, which I don't know if mine's going to do. But you can let it dry flat. Okay, so the question would be that your students would be interested in and you want to direct your students towards is, what is the difference between the black paper before you put it in the nail polish and after? An easy difference that they'll see is it has this optical property of iridescence. It has multiple different shining colors and this really kind of neat oil slick sheen to it. So your job is to explain why is this happening and why is it nanoscale science. So I can help you with that. The optical property of iridescence itself in nature is actually pretty common. You see it in butterfly wings, beetle shells, mother of pearl inside of clam and other organism shells, pearls, and of course our lovely peacock feathers as well. Nature is very good at doing nanoscale science, whereas we are kind of catching up with nature on assembling things on the nanoscale. This process, or this outcome, the iridescence that we see in nature, is actually an optical property, and it's due to nanoscale thin films, which is actually what you've created on the black pieces of paper here. It's important to point out to your students that iridescence, unlike other colors, is not caused by dyes or pigments. This is solely due to the interaction of light with a thin film, either on the pieces of paper or in the biological processes in nature. Remember, the nail polish is clear, and remind your students that the nail polish is clear to start with. It doesn't look iridescent or pretty or have multiple colors in it when you start out. It's only when it spreads into a thin film over the layer of water that it takes on this iridescent characteristic. And the layer is on the nanoscale, and that's part of the reason why it's reflecting like that. So in this example, we're not actually causing the paper to take on color. We're just creating the property of optical iridescence. And optical iridescence is caused by the interference of 2 different sets of light waves. And your Nano Days kit will include this card on background information. I'm going to put it right here so you can see as I talk about it. And it has a really nice breakdown of the visible spectrum, waves, and the crests and troughs of the waves, and also this diagram, which is important to explaining this concept, or for explaining this concept. So what happens in iridescence is that two different sets of light waves interfere with each other, either constructively or destructively. If they're interfering constructively, it creates the iridescence property. When they interfere destructively, it creates the dark zones, or the zones of shadow that you see on this. Okay. So there are two different sets of waves that come in. The wave that comes in and bounces off of the top and comes back, and then also waves that penetrate through the film all the way to the black paper on the backing and then bounce back. If the waves bouncing off the surface and those bouncing off the paper interfere constructively, then light shines brightly back from the surface. And thin films with their thicknesses that are in the visible part of the spectrum, which a refresher is 400 to 700 nanometers, can create some special color patterns depending on the thickness of the films and the variance in their thickness. So when the light reflects back, it shines in colors that reflect the thickness of the thin film, and the variance in those colors show the variance in the thickness. So when you have those patterns and bands and regions of different color, those show different thicknesses in the nail polish thin film. Areas that reflect no light or do so only weakly are areas where destructive interference is taking place, where the two waveforms are subtracting from one another, where crest and trough are overlapping and they subtract to a net zero. All of it makes a really pretty effect. Your students will enjoy having their new little nano bookmarks with their nano thin films, and it's all because of science on the nanoscale. So the next activity we'll move to is the tiny teacups activity. Okay, in the last activity, one of the main take-home points as far as nanoscience goes that you want to make sure your students understand is that behaviors of materials on a nanoscale frequently are different than they are on the macro scale that we're used to. So clear nail polish becomes multicolored when you stretch it into a nanoscale thin film, and that's because of the interference and the actions of the interference of the thin film with light. In this one, you get a chance or an opportunity to show your students that there are other ways that things behave differently than we expect on the small scale. So this is the tiny teacup, and this is exploring forces, predominantly surface tension and gravity. So the two concepts you'll want to make sure that you cover with your students, either in advance or explain while you're going through this activity, are the forces of gravity and surface tension or surface cohesion of molecules. So this activity, again, reiterates one of the major points of nanotechnology research, which is some things behave differently on the nanoscale than we're used to observing on the visual or macro scale. An example of this is gold. You can find research about this, and it's fascinating to read up on. But basically, on the macro scale, we all know what color gold is, right? It's that metallic, shiny yellow color. But if you take gold and you grind it down or create particles that are like 25 nanometers on the nanoscale, gold will actually appear red, because it interacts optically different at that size. You can also get gold to appear blue or yellow depending on how fine you make the particles. So this is just one example of how size affects the behavior of materials. In this activity, it's going to allow you to discuss how the size of a material affects its behavior in a way that your students can actually see and play with. So you'll have your students pour water out of two different cups and ask them to describe the results. So this one is very easy. This is a standard teacup, and you say, what do you observe? Well, the water pours out simply. The other one is more interesting. This is the tiny teacup, and I will zoom in on this. Is it going in? Okay. There we go. We'll let it focus a little bit. That's much better. Okay, so this is the tiny teacup. It is very difficult to manipulate, but there it is on its side, and here it is like this. Okay, So the tiny teacup, you don't need the big tub of water because it is indeed tiny. What you'll have your students do is use their little dropper bottle and fill this teacup with water. Really, 1 or 2 drops will do. And then you will have the students try and dump the water out. And what you will see, if you can see on mine, is even when I tip it, no water comes out. Okay. So, what's happening? Well, we know when we use this activity that gravity pulls the water out of the cup. When we do this activity with the tiny teacup, surface tension dominates and trumps the force of gravity. On the macro scale, we all know gravity is an important and dominating force. On the nano scale, gravity of course is still present, but it has a smaller impact on these very small things. So a good way to think about this is that gravitational force is partially dependent on the size or the mass of the object, actually. And the mass of nanoscale objects are very, very small. So that allows other forces like surface tension, which is molecular attraction between 2 molecules, water molecules in this case, that allows surface tension to trump the activities of gravity, which is something we're not really used to thinking about on the macro scale, but it's something that's really common and pervasive on the nanoscale. So, you may recall that water is a polar molecule. This is why the water is attracted to the other water molecules. One side of the water molecule has a positive charge, the other has a negative charge. And so this increases or causes molecule cohesion, which results in this process of surface tension. So the water stays in the tiny teacup because on the smaller scale, force of cohesion trumps the force of gravity. Another great activity to do this that most students have either done or had experience with is the how many water droplets can you get onto the surface of a penny. But what you want to do is set up a small scale versus a large scale demonstration of it. So a good way to do this is you set up the penny and the students are given an eyedropper or a bottle like this, and you challenge them to see how many drops they can get to stay on the surface of the penny. And they'll find that way more drops stay on the surface of the penny than they would expect, because as they build up a little bubble or a layer on there, surface cohesion starts to become an important process and it holds the water in place. So the larger scaled up version that does not work of this is get a relatively flat plate and a turkey baster and use that as your analogy for here's a circular flat object and an eyedropper. Here's a circular flat object and a turkey baster, which works in the same way as an eyedropper. And students will find that when they scale it up to a larger size, that the same properties do not dominate and that gravity dominates in that. So that's an activity that you could kind of extend in your classroom to further demonstrate the idea that on the nanoscale, things behave differently than they do on the macro scale. And all in all, the tiny teacup activity gives a clear demonstration of how size affects the behavior of the material. And nanoscience researchers use unexpected size-dependent properties of different materials to develop new technology and then also to improve existing. So that is your tiny teacup activity. Next, we will move on to everybody's favorite Nano Sand. All of these activities have information on NICENet, the National Informal Science Educators Network, which is found at nicenet.org. And you can find all of this, and including Nano Sand actually has a particular demonstration video that NICENet has put together, which is outstanding, and I would recommend looking at that if there's anything that you're not clear on after we talk about it here today. Okay, so there are a couple different ways to go with Nano Sand. Your Nano Sand may be a different color. It's also known as Magic Sand. I think that's the trademark name for it. My Nano Sand is yellow, and then so on the left is the Nano Sand, on the right is regular sand. Some of the concepts you might want to cover in some level with your students is the idea of hydrophobic and hydrophilic. Although that's key to really understanding in depth what's going on, most students, and I've done this activity with preschoolers as well, are okay with just knowing that something about the nano sand repels or pushes water away. And that's certainly an adequate explanation. The goal is to get the students intrigued and interested in the science properties by doing something fun with it. So there are a couple different things that you can do with Nano Sand. This is the one that I do at Nano Days, and I'll put these trays over here. And I need an eyedropper bottle. Okay, so I need to zoom out. Okay, so these are my 2 trays of Nano Sand, and I will zoom in a moment on them a little more, but just so you can see, the trays are nice to work with because as you look at the Nano Sand and what it does with water, those properties will become a little more evident. So first, we'll look at regular sand. Most students have an innate ability to understand what's going on with sand because they've spent so much time playing with sand in their lives. So here's the regular sand, and the thing you want to ask them is, if I drop water on the sand, and have them do it, not you, but drop water on the sand, and what will you anticipate happening? And of course, the water absorbs into the sand. Okay? Doesn't do anything exciting, new, or different. Nano Sand will be a contrast to this. So then we do the same thing with Nano Sand, and I'll zoom in so hopefully this is a more visible process. Okay, there we go. So ask them the same question. What do you think will happen when you drop it on the yellow sand? And what they will discover is water behaves very differently when it's on Nano Sand. It refuses to sink in, and that's because of this hydrophobic layer that is on the sand, okay? And so you can do lots of cool things. You can roll this around. You can challenge students. Students always want to try and figure out how they can beat the system, so you can challenge them to smush the water in. What happens? They still cannot get the water to absorb in the Nano Sand. If you're playing with this all day and you're doing multiple sections of your class with this, towards the end of the day, the Nano Sand actually will start to absorb more water. So what you'll want to do is hold a little of your Nano Sand in reserve so that you can refresh it later. I've found that when we do Nano Days, that after hours and hours of playing with this, the Nano Sand will start to absorb. Okay, so that's one way to play with Nano Sand, and I'll explain what's going on in a moment with that. When you're working with your students, a good thing to do, especially if they're putting a lot of water on the Nano Sand, is just take a sponge and use a sponge to dab up the water from the Nano Sand, and that'll work just fine. Okay, another thing to do with Nano Sand that demonstrates basically the same principle and I'll get this here. Zoom out a little bit. There we go. All right. So another way to demonstrate something cool about Nano Sand is to show Nano Sand this way. What you do is take normal sand first and foremost and sprinkle it on the top of water and observe what the result is. Okay, the normal sand, as we expect, sinks right to the bottom, right? Then take Nano Sand and do the same thing. And what you'll notice is as long as it's in small quantities, the Nano Sand's going to stay mostly on top. Furthermore, as I tilt this, you might be able to see, the Nano Sand actually will start to accumulate together. And when you finally exceed the threshold of its ability to maintain surface tension, Nano Sand, which is pretty substantial, Nano Sand will start to sink to the bottom, which I still haven't gotten it. And there it goes. And it's fascinating when it sits there on the bottom because you can see that it's insulated itself from water and is refusing to interact in any way, shape, or form. And this is really neat, and students love this principle and this activity for that very reason. So the question is, what is going on with Nano Sand? Why is it behaving this way? Well, Nano Sand grains are coated with a special silicon-based compound. One end of the compound is attached to the sand particle. However, the other end of the compound is hydrophobic, which means it pushes away water, and it sticks out away from the grain of sand. So this creates a nonpolar or hydrophobic layer on the surface of each sand grain, and this layer repels water from individual sand grains, which results in the very cool processes that we see here. It's an example of how nanoscale engineering can change a material's behavior or appearance at the macro scale, even though it's micro or nanoscale technology and engineering with it. So treating the surface of individual sand grains of sand makes a new type of material that behaves very differently than the regular beach sand would and what you would be used to with regular beach sand. So nano sand actually, or magic sand actually started out with a practical industry application, and it was developed actually to work with oil spills. So I'll show you a demonstration you can do with your students that shows this application of it. And this is really neat, but keep in mind you want to save this for the end because this absolutely destroys or makes your nano sand no longer usable in the process. So I'll try and get a good view on this. So scientists found a way to take advantage of hydrophobic properties of the nonpolar materials like the magic sand. And magic sand was originally developed for cleaning up oil spills. So I brought a little oil in to demonstrate this. This works really well with not just standard petroleum-based oil, but it also works really well with vegetable oil as well. So if you don't want to bring oil into school, that's certainly understandable. So what happens is the sand bonds with the oil. I'll put a little oil in here and create my ExxonMobil oil slick. And let's see, we can see the oil sitting on top there. Great. And so the sand bonds with the nano sand, as you'll see here, bonds with the oil that's floating. And if you put enough of it in, it will sink the oil to the bottom and latch onto the oil and hold on to it. So I took part of the oil slick out of the way, and then if you keep continuing to add it, it bonds with more oil. And I'm just going to go a little crazy here and put a lot in. And boom. Now we've taken the oil predominantly off the surface and we sunk it to the bottom, and the idea is that the oil company would dredge that up and put it through a filtering and recovery process and be able to recover the oil. Unfortunately, the process requires, as you saw, large quantities of magic sand to do that, and that made it cost prohibitive. However, if the price of nano sand or magic sand decreases, it might be more popular for environmental cleanup, and it's absolutely a useful tool for this in this capacity. Magic sand's also been used to protect electrical and telephone wires in cold climates. When they lay telephone and electrical and optical wires, they're buried underground to protect them from extreme temperatures. However, when groundwater freezes around them, that damages those wires. So what they'll do is they'll put a layer of magic sand around that, and that hydrophobic layer will repel water and keep it away from the wires where it freezes and causes damage. So there are industrial applications that are already developed and out there for these nanotechnology. Again, nanoscale engineering changes the behavior of these objects, everyday objects on the macro scale. So that's nano sand. Next, we'll move on to balloon scents. I've actually cheated a little bit and already blown up some balloons with the scents in them. The concepts you'll want to be able to cover either in advance or with your students when you do this activity are the concept of what is a molecule. Molecules are on the nanoscale. And also, what is the process of diffusion, this movement of molecules from an area where they are highly concentrated to an area where there is low amounts of concentration. So this activity will take probably most of the prep time. The nice thing is if you're doing multiple sections, you blow up the balloons once at the beginning of the day, and they'll work for the rest of the day. Follow the directions that are given in your kit as they go, but basic summary is that you add scented extracts to the balloons and then inflate them and tie them off. Keep in mind these are latex balloons. Your students may have latex sensitivity or latex allergy. That's something you'd want to ascertain prior to doing this activity. So determine if that's a factor before you get going. Once you have the balloons set and inflated, you basically just have the students smell the balloons. And what they do is try and identify which scent is which. So here we have orange extract and coconut extract or vanilla extract, whatever scents are provided to you and whatever scents you want to put in them. I usually give my students a list. Here are the possible scents. Which color balloon do you think has the scent? Is the pink one the one that has the vanilla? Is the purple or the red? And so on and so forth. And then, of course, you hopefully would keep a master sheet so you know at the end of the day which one's which. After everyone is finished with the balloons, you can ask them, which, focuses them on the fundamental important learning activity here. If the balloons have scent sealed inside them, how come they can still smell them? So what the actual science behind it is, and this won't be a surprise to any students that has actually pondered why a helium-filled balloon deflates over time and has some sort of clue as to why that happens. But tiny scent molecules, which are on the nanoscale, are escaping out of tiny pores in the latex. The pores are also on the nanoscale. And then they're reaching your nose where they're identified by your body as a particular scent. This results from diffusion because the concentration of scent molecules inside the balloon is higher than the concentration of scent molecules outside the balloon. So you get diffusion out of the balloon into the surrounding environment. Pores in the balloon and scent molecules are both on the nanoscale, which allows diffusion to occur relatively easily. This same process is the reason why a helium-filled balloon deflates over time. Helium, actually, we know is the second smallest atom, so that really is very, very tiny on the scale of latex. Those pores are easy for it to escape out of. So that wraps up all the activities. I encourage you to do these activities with your students. Nanotechnology research is changing and will change the way that we live our lives. And better that they get exposure to this technology and these concepts on an early level than later. Thanks a lot for your attention, and enjoy Nano Days Kit.